My name is Irina Tazar. I'm a staff scientist at Sandia National Lab, and I'm the chair for the group that organizes these webinars, which is the U.S. Association for Computational Mechanics, Energy and Earth Systems Technical Thrust Area. And so we, the topics we cover are quite broad, listed here, from climate to geomechanics to wind, solar, nuclear energy to carbon sequestration, oil, gas recovery. And besides these webinars, we organize other events like thematic workshops every couple of years. So yeah, I would encourage you to join. If you're a member of USACM, joining the TTA is free. If you're not a member, joining USACM gives you benefits such as discounted rates at conferences and workshops that are organized. But in any case, you're welcome to follow our LinkedIn page. I usually will announce events there. So everyone who's a member, whether or not they are officially in the TTA, can see those. So this is our third seminar in our fall seminar series. So this seminar series, this particular instance, is devoted to talks by postdoc and early career researchers. And so we're going to have one more of these after today. It will be on Tuesday, December 9th, by Dr. Nicola Retz, who's a postdoc at UT Austin, who will talk about some UQ for ice sheet simulations. And so with that, let me go ahead and stop sharing. It's my pleasure to welcome today's speaker, Dr. William Radünz from Johns Hopkins University. William is a postdoctoral researcher at the Whiting School of Engineering's Ralph O'Connor Sustainable Energy Institute. He has a PhD in mechanical engineering from the Federal University of Santa Catarina in Brazil. He has been working on wind energy for more than 10 years. His work focuses on understanding the interactions between offshore wind farms and the atmosphere, particularly developing parameterizations for numerical weather prediction and climate models. In the past, he explored how terrain influences wind resource variability and impacts wind farm performance. And more recently, he has delved into multi-scale large-eddy simulations of stable boundary layers and low-level jets as part of the American Wake experiment, or AWAKEN project, led by NREL. So I think we'll be hearing about some of that today. And his kind of future goals are to establish a research group dedicated to advancing wind energy technologies and advancing the challenges of wind energy and atmospheric interactions. So since he's a postdoc, I assume if anyone here is at a university or a lab and is looking for someone to establish such a group, William would be a great person to connect with. So with that, I'll hand it over to William. You can go ahead and start sharing.
Thank you, Irina. Thank you for the introduction. It's my pleasure to speak to you. So today I'll talk about the work I've been doing in the last 2 to 3 years. So there's very recent work and more mature work. And it all converges to the multiscale simulations of atmosphere wind farm interactions, especially the role of spatial gradients and how they modulate the power performance of wind farms and the wake recovery of wind farms. Some brief personal background to understand where this work came to be. So I was a postdoc at the University of São Paulo in Brazil for 2 years. And last year I started a postdoc at Johns Hopkins University in the US. And during my postdoc at the University of São Paulo, I started my interaction with the AWAKEN experiment, which I'll talk about briefly. So the talk today is kind of split into A and B. A will deal with how the spatial gradients modulate the wind farm performance, and that's work related to AWAKEN. And the part B is the work I've been doing at Hopkins in Julie Lundquist's lab, which is also focused on spatial gradients, but rather how these spatial gradients modulate wind farm wake recovery. You can notice there's some nice symmetry here, but I like to raise awareness that the symmetry isn't perfect because the spatial gradients in A and B are not the same gradients, but we'll see more about them soon. So let's begin with the part A and the role of spatial gradients in modulating wind farm performance. So the diurnal cycle of atmospheric stability over land usually follows this pattern. In the top figure, we have in the x-axis time and in the y-axis height. So blue means the boundary layer is statically stable, which means that the cold air is closer to the surface than above. And the red color means that the warmer air is closer to the ground. So what happens when the warmer air is closer to the ground? Well, it rises because of buoyancy, because it's lighter than the air around it. So that creates convection, that creates turbulence. So the daytime winds are usually more turbulent because of this process. But when the sun sets, then the hot air that was in touch with the terrain surface, and now the terrain surface begins to cool by emitting long wave radiation. And it begins to cooling, and then the overlying air begins to cool, and then we have a stable boundary layer. So that's the difference. And the two types of boundary layers create tremendously different winds, as we'll see. The stable boundary layer has a particular case, I think we can call it, which is called the nocturnal low-level jet. You'll see in the literature there's all kinds of mechanisms that create low-level jets. They flow over sloping terrain, frictional decoupling, transition from the ground toward the ocean surface. But in essence, a low-level jet can develop once you have a stable boundary layer. Because why stable? Because stable has low turbulence, and low turbulence creates low friction, so the layers of air can slide freely. So that creates this dashed profile, which has a strong wind shear with height. And from on one hand, for wind energy, that's important because it creates strong winds. So that is good, but there's some problems because the low-level jets, first, they make the turbines operate under strong wind shear, so the blades will suffer from stronger blade fatigue loads. And also, the very high shear can trigger turbulence bursts that can be violent and damage the fatigue life of the turbines. So that's why it's important to study low-level jets. Now, there's another piece of the puzzle, which is terrain effects. So here we have a hill. The flow comes from the left toward the right. And if this normalized wind speed is lower than 1, the flow decelerates, and it's greater than 1, the flow accelerates. So we can see the flow decelerates a little bit upstream of the hill, but as it approaches the hilltop, the wind speed increases and reaches the maximum at the hilltop. So this happens for neutral conditions. The wind speed is usually maximal near the hilltop, and we all have the intuitive sense of this fact. When we climb to the top of a hill, of a sand dune, the wind is usually strongest there. Okay. Now there's two important things here in terms of the grand scientific challenges in wind energy. There's this paper that was published a few years ago, and it established that the first challenge is understanding atmospheric and wind power plant flow physics, which I colored blue here. And in one of the sub-items of this first challenge, it mentioned mesoscale, microscale coupling, offshore and complex terrain, which I colored in red. So now let's situate some important endeavors that were made in the last few years on these topics. The work here is focused on the AWAKEN, but now I want to show a little bit the way that the scientific way that paved the way for AWAKEN. So a few years ago, we had a very famous Perdigal experiment, which is part of the new European Wind Atlas. So it was a large-scale measurement campaign focused on wind energy, where they measured the wind flow over complex terrain. So the science was very focused on wind flow over complex terrain. The problem is that there wasn't a wind farm operating in the area, so that's the focus of that experiment. And this is also the motivation for the AWAKEN, because the focus of the AWAKEN is the atmosphere interacting with the wind farms, not over complex terrain. And in Oklahoma, where AWAKEN is taking place, we have all kinds of processes. For instance, we have wind farm wakes, we have wind farm blockage, farm-induced gravity waves, and we also have southerly low-level jets in the area. So we have a lot of interesting phenomena from the point of view of science. What is a site of simple terrain? So the American Awake experiment, you can see on the right, that's the site location. The black dots are wind farms, so it's a cluster of wind farms in Oklahoma. And the red dots are sites where measuring devices and scanning lidars and so on are deployed, radars. So AWAKEN is a project funded by US DOE and led by 4 US national labs, NREL, Sandia, PNNL, and Lawrence Livermore, but also some universities, mostly from the US, but some European, and also the University of São Paulo in Brazil, have joined to tackle some of these scientific challenges. Here, for instance, there's one of the red dots, there's a lot of instruments already. There's lidars, scanning lidars, sonic anemometers, and many other measuring devices. So there's a lot of evidence to support the scientific questions that need to be addressed in terms of wind energy. From the many testable hypotheses in AWAKEN, I noticed that not a single one is focused on terrain. The terrain is mentioned, but there is not a focus on terrain. And I always like terrain, so I think that was a good opportunity to see how the terrain affects the winds and the performance of wind farms, and also possibly plays a role in the other testable hypotheses, even if indirectly. So that's what this work's about. Now, I talked about simple terrain and complex terrain, and I want to show you with numbers what's the difference between simple terrain and complex terrain. So here we have a part of the AWAKEN area in Oklahoma is a 40 by 60 rectangle, and the maximum variation in terrain elevation is 150 meters. Now I'm going to show to you a complex terrain site where there's an actual wind farm. So it's a much smaller box, it's 20 by 20 kilometer, and the maximum variation in terrain elevation is 500 meters. So this is complex terrain. It's a dramatic difference. So the wind will feel much more this terrain effects because of the changes in elevation are much more aggressive. But our goal is to see if this more smooth terrain can have a role in the wind. Zooming in near the wind farm area that we'll be studying, we have the rain profile here, and here the height above ground. So within the wind farm that we're studying, there's a change of elevation of about 20 meters over 5 kilometers. And this is it's very, you wouldn't feel, I think, the difference in elevation considering this distance. So it's a very simple terrain. So our research questions is, can simple terrain influence how the winds vary in space and wind farm performance? And are the low-level jets more sensitive to terrain-induced effects than other types of boundary layers? So here we are the AWAKEN site in Oklahoma, north of Oklahoma, this red triangle. Let's zoom in. We have the wind farms that we've seen before, and our focus would be on the eastern portion of the King Plains wind farm. And because we're studying a southerly low-level jet, we want the low-level jet to hit the wind farm, and that the wind farm doesn't feel the wake effects or the blockage from any other wind farms. So that's a good thing. You can see there's this patch of land. There's no wind farm, so the wind will hit at least the first row of turbines without being disturbed by the other. To do these simulations, which I'll detail in a second, we use the weather research and forecasting model, which was usually a model to run at the mesoscale grid resolutions, but over time it became also capable of running simulations at very high resolution. But in essence, it's a numerical weather prediction model. It solves Navier-Stokes equations of fluid motion, mass, energy, and moisture conservation in 3D space and time. Some of these things can't be solved directly, so it parameterized a lot of physical process related to evapotranspiration, radiation, cloud formation, and so on. So it has a lot of rich physics embedded in the model. So here we go. We have a computational domain that is positioned. It contains the AWAKEN site, but it contains much more area around to resolve the wind flow everywhere. The input data is from the high-resolution rapid refresh model, which has a spatial resolution of 3 kilometers, which is a relatively high spatial resolution. And then we have a mesoscale domain at 1 kilometer resolution. And now we're going to nest another domain within this one to increase the resolution a little bit. So 100-meter resolution, it's closer now to the wind farms that we're studying. 100-meter resolution. And there's another nest, which includes a portion of the wind farm that is represented at very high resolution. And here we can see the turbines. The distinction in terms of turbulence parameterization is that the mesoscale domain uses the USU PBL scheme. So it basically doesn't resolve turbulence, whereas these two domains are large-eddy simulations. The innermost domain uses the NBA model as the subgrid model for the LAS simulations. And okay, now let's take a look at this domain that has the turbines. So the wind comes from the south. The first thing, we need to spin up turbulence in this very high resolution domain. So we apply the self-perturbation method near the edges of this domain. So it accelerates the transition from a smooth flow to turbulence. So we have these eddies going on before they reach the wind farm. The wind turbines are represented as generalized actuator disks. So their effects on the flow are felt, and the wake effects are represented in the simulations. And we also have land use data at very high resolution. If you look here on the right, there's some vertical and horizontal lines that were at first we didn't know what those were, but later on we found out that's actually a train track and roads. So there's very high resolution in the way we force the simulations. They were run on NREL's now retired Eagle and Kestrel HPC. A single simulation to simulate the wind farm interacting with the wind for 1 hour. It takes about 3 to 4 days with the 1200 CPU cores. So it's a relatively expensive simulation. And this is our focus time, April 3, 2023, between 4:30 and 5:30 UTC. So that's close to midnight local time we're talking about. Okay, so let's take a look at how the wind represented in the simulations compares against the observations. We see good agreement in the wind speed profile in the left, except for a few heights where there's some deviation from the observations, and the wind direction is even better than the wind speed. So we're simulating the wind speed that actually occur there accurately, and this is important. We can see that near the lows of the low-level jet, the wind speeds reach about 90 kilometers per hour. So that's a storm level wind, whereas near the ground, we would be feeling perhaps a gentle breeze. So it shows what's the power of the low-level jet. And here on the right, we can see that the turbulence is actually well resolved by the simulations. So it means that our approach was effective in simulating both the mean flow and the turbulence. Now let's take a look at the wakes. You can see here the first row of turbines, then the second and third row, feeling the wake effects of the front row. And the turbulence seems okay in the simulations. So that's the wind speed at hub height at 90 meters above ground. Okay, so we can take those instantaneous wind speed and average. So on the left, there's the average of that video that I showed you. We also did a simulation. Everything is the same, but without the turbines, just to see how the wind behaves without the turbines, which is the plot in the middle. And then subtracting one from the other, we have a difference, which is the wind speed deficit, which shows very clearly the wake effects in the simulations. So we also have the model also computes the instantaneous turbine power for each turbine, and we also had the SCADA data from each of the turbines. That's the turbine production data, actual turbine production data, and we can see that contrary to the expectation, the turbines in the first row, which don't feel the wake effects, actually produce less power than the turbines in the back, which do feel the wake effects, which is strange. But both the simulations and the SCADA data agree on this feature. So that's an interesting thing to further dig in and see what's going on. So before that, let's look at one more video. So simulation on the top has turbines, and on the bottom, the simulation doesn't have turbines. So you can see that the core of the low-level jet looks a little bit closer to the turbines in the back row. It may not be so clear here, but let's move on. So that was instantaneous again. So now let's look at the average. These are north-south transects, slices, looking at the wind and how the wind relates to the terrain. So this is the mesoscale terrain. And you can see that the maximum wind speed, which should be yellower, doesn't occur at the top of the elevations. It occurs slightly shifted downstream from the top of the elevations. Here one, here another one, another one, another one. And early on, I had told you that the wind speed would be maximal at the hilltop. So what's going on here? And when we look at the second domain, we can see more clear. So here the topographic feature and the maximum wind speed shifted downstream. And here near the wind farm area, the same thing again. So to understand this, we actually need to go back in time to 1955 to Robert Long's laboratory. So in 55, so this is not a new thing, they did an experiment. So there's an obstacle, there's water, and salt was carefully mixed to this water in such a way that there's the density, there's more salt near the bottom than above. So the fluid here is denser. And then they have a stick and they can slide the obstacle and create this flow here. So let's assume the flow is coming from the right to the left. So the first thing that we see is there's this ondulation. So the flow comes here and then goes up and then goes down and then goes up. And this happens because the denser fluid, the dense fluid flows down and then it finds essentially the denser fluid, which pushes it up, and then it goes up and then it finds itself in a surroundings that is lighter, and then it goes down and so on because of the buoyancy forces. And this is called the internal gravity wave. And you can also see that the wind speed is not maximum at the hilltop, is slightly shifted downstream. So this can happen with the stable boundary layers, and the low-level jet belongs to the stable boundary layer. So that's what we have. So going back to our work, these ondulations that we see in the flow field, that those are gravity waves, and they happen because the flow is stably stratified, and then it interacts with the topography and causes these features. And then the wind speed is not maximum at the hilltop, but it's shifted downstream a little bit. Okay, so this top plot, it shows, it computes the difference in the wind speed. So we have the profile of wind speed in the first turbine here. That's the reference. And then we subtract the reference from everything. So the red means the wind speeds are faster than in the first row. When they're blue, it means that the wind speeds are in that same layer. The winds are weaker than in the first row. So across these three rows of turbines, you can see a difference in wind speed that can reach 4 meters per second. And that's a lot of wind speed in terms of wind energy. And again, the terrain is very simple. But why is it that there's this red bubble, then white, and then blue? Why is this stratification of the spatial variability in wind speed? To understand it, we need to remind of the structure of the low-level jet. So the low-level jet has strong wind shear, so the wind speeds vary a lot with height. And in the simulations, we identified that the streamlines, they're actually displaced when they interact with the terrain. So near the third rows of turbines, the streamlines get displaced sometimes more than 50 meters. So let's look at what happens when specific layers of the low-level jet are displaced. Below 300 meters, where the wind shear is high, if the wind is displaced down, then stronger winds will be now at lower levels. So that's an acceleration. And near the low-level jet nose, because there's a small change in wind speed between layers, if one layer of air is displaced down, it will create a small change in the wind speed. So the white means, and the white layer coincides with the nose of the low-level jet, where there's almost no wind shear. And the negative part of the wind shear, that's where we see this decrease. So the low level jet is displaced down and it decreases the wind speed at that layer. So to summarize, so the simple terrain can influence farm performance, and it can, especially during low level jets, because the low level jets have this characteristic of, we've shown the mechanism of the displacement, the vertical displacement of the streamlines, and because the low level jet has tremendous shear, then that creates strong horizontal variability in wind speed. We also saw that the state-of-the-art models, including multiscale simulations, they can simulate even the performance of the wind farms. And this unusual performance agrees with the SCADA. So that's a good progress. And also the observations are very important to validate and improve the models. For instance, if we didn't have the very good information from the lidars at the A1 site, we wouldn't know that the wind we were representing was accurate enough to study the turbine performance. So that's a prerequisite to study turbine performance. So it's a great thing that we have AWAKEN. Okay, so that was part A, the influence of spatial gradients on turbine performance, the weird turbine performance. Now let's look at the spatial gradients and wake recovery, and let's move to a place completely different. Let's go to the sea. So a great motivation to study wind farm wakes are in the offshore environment. Why? Because the offshore environment is packed or planned to be packed with the wind farms. So there will be many wind farms in those areas. But the offshore environment has much lower turbulence intensity than over land, which means that the wind turbine wakes will take much longer to recover. So the wakes will persist for tens of kilometers and so on. And thus the wakes from some clusters of turbines can impact other clusters. And it's important to understand this process. So let's consider two scenarios here in terms of numerical modeling. Here on the right, we have a situation where we have an upstream wind farm and then the wake in gray and then downstream wind farm in blue. If our model represents a slow wake recovery, artificially slower wake recovery, it will produce a stronger wake, and thus the wake losses in the downstream wind farm will be exaggerated. And there's some evidence in the literature that there is indeed a slow wake recovery in mesoscale simulations when they're compared to LAS. So that call us our attention. Okay, so in this study, we use the Fitch wind farm parameterization. And the Fitch wind farm parameterization, it has two terms. This one in the left is the momentum sink term, and the one in the right is a TKE source term. What the momentum sink term does is, because the mesoscale simulation usually run with grids that are greater than 1 kilometer. So in 1 kilometer, you can have a few turbines. It won't resolve the rotor of the turbine. So let's suppose we have a grid cell that has 3 turbines within. So what it will compute is like, what's the momentum sink these 3 turbines would have within that grid cell. And there's no, it neglects the wake effects that can happen between the turbines that exist within the same grid cell. So it removes momentum in the parameterization, but it also injects TKE in the parameterization. So, and how it does that? It has all these terms here. And especially to us is the TKE factor alpha. So if alpha is 0, it will say that there's no TKE added by the wind turbines within that grid cell. And 1 is the maximum allowed value in this implementation. So it will inject a lot of TKE. And it has to inject TKE this way because it doesn't have spatial resolution to resolve the turbine rotor, then turbulence develop, and then TKE develops, etc. So the question is, comparing mesoscale wakes with LES. So numerical weather prediction with the wind farm parameterization underestimates wake recovery compared to LES. And if so, what are the causes for this underestimation? That's the questions we want to address. So we have a large-eddy simulation from the work of Casper et al. From the University of Twente, who are partners in this work. So they joined us. We're using their LES data. So their simulations, they simulate the turbines as actuator disks. They use 50, 20, and 10 meters. So the grid is not equal in all directions. And here we can see the averages of wind speed for a sample of their simulation. And then we try to do as good as we can the same thing with the in WRF with the wind farm parameterization. And to do that, we use version 4.4 of WRF. As I said before, we use the Fitch wind farm parameterization and with a new correction to the induction of the turbines, which is important. The grid resolutions are totally different from the LES, so we tried grids with 346, 890, 1246 meters, which are much coarser in the horizontal resolution. But on the vertical resolution, we use 10 meters, so you can see that the vertical resolution is the same in both simulations. And looking at the results on the lower left, you can see the totally different character and resolution of the mesoscale simulations. Okay, so how did we spin up these simulations? We have two domains. An outer domain in black runs with the periodic lateral boundary conditions. So the flow recycles until the desired PBL characteristics are reached. And when the desired characteristics are reached, then an inner nest domain is turned on, and the results from the parent domain are mapped onto the laterals of the innermost domain, and this innermost domain has the wind farm. So that's how we do to avoid the wind farm wake being recycled and so on. So zooming in, we have 60 DTU 10 megawatt turbines. And you can see that we were careful to position one turbine within each grid cell. So the grid cell is made to ensure that no two turbines occupy the same grid cell, because again, the parameterization doesn't compute the subgrid wake effects. So that way we can avoid this. Okay, so we're simulating a condition typical of the offshore environment. It's very low roughness, then it's 0.002 meters. Latitude associated with the North Sea, based on the work of Casper et al. And it's a neutral boundary layer, idealized neutral offshore boundary layer. So you can see here in the potential temperature profile, it's a boundary layer of about 1 kilometer, and then there's an inversion, and it goes. You can see that LES matches well our simulation in blue. And the way it is, you basically guess the initial condition of the overall simulations, for instance, wind speed and direction. And then the simulation develops, and after 26 hours, then you have like the wind speeds that you desired, near 90 meters per second at hub height, and basically westerly flow. So you have to iterate a few times, change the initial condition, and then run again until you get what you want. We did a few sets of simulation. There's the baseline case with 1.2 kilometers, which is about 7 rotor diameter in spacing. Alpha is 0.25. That's a value that is usually being considered the standard in the literature. And then we have a set of simulation where we vary the alpha parameter from 0.50 and so on. And there's another set of simulation where we only vary the grid spacing. So comparing the profiles of wind speed and direction, the agreement is excellent. And that is great because we want to remove the inflow variability from the discussion and focus on how the wake effects are represented. Potential temperature, nice. And even the TKE is very well represented. So the TKE matching well between both simulations means that it's a consequence of the wind shear and veer also matching very well. First, we need to coarsen our simulations so we can compare to the LES. And we did that by using the base case as the reference. So basically, we spatially average the LES simulation based on the base grid, and then we got the coarsened LES. Now we will average in the y direction these results at hub height, wind speed, and TKE in such a way that we have the streamwise a streamwise variation of wind speed and TKE for all these cases. And that's what we have here. So we have the wind speed, and we have several cases here varying the degree of the TKE that is added, and black is the LES. So here is the intra-farm region. So that's the region where the wakes are developing. And then we have the near farm wake in green, and then the far wake in blue. So what we can see here is that usually in the simulations, the amount of momentum being extracted is greater than in the LES. And this happens because of the coarseness of the grid. So because the grid is coarse, the wake effect is spatially average. So the wind turbines in the mesoscale simulations, they don't feel sharp wake effects. And in that way, they can extract more momentum. The LES, because the turbines feel this very sharp wake, it limits the amount of momentum they can extract from the wind farm. And that's why these extract more momentum from within the wind farm. Now let's look at the near farm wake. So that's one process. In the near farm wake, you can see in the LES that there's this little bump here in black. So the wind speed density starts to recovering quite fast here. And you don't really see a bump in the WFP simulations. So the wake recovery is underestimated here. So we have these two things going on. And when you look at the far wake, the rate of change of the wind speed is very similar. So the representation of the physical process is good there. Now let's look at high resolution. At high resolution, that's interesting. You can see that in the purple line, the momentum is extracted more accurately. In the gray line, which is a simulation at high resolution with more added TKE, it matches even better the LES. The wake recovery is also a little bit better than what we saw. So it seems that having a little bit more of resolution can improve this process. Okay, so now it's time to understand why this happens. And the lateral turbulent momentum flux is associated with the wake recovery. So we can, using K-theory, this momentum flux can be substituted by an added viscosity and delta wind speed delta y. So when we compare these two cases, we can see that the LES in black, there's some spikiness in wind speed, and that's the sharp deficit that it represents. So because the mesoscale simulations don't have this sharpness, they will underestimate the wake recovery because of del U, del Y aspect of it. Now let's look at the vertical direction. In the vertical direction, we see a similar feature. The black line here has a much stronger gradient than in the mesoscale simulations. And so this vertical momentum flux will also be underestimated. So we can see that in both directions in the mesoscale simulations, this is being underestimated. And there's a final aspect of it. When we look at the TKE, the streamwise variation of TKE, you can see that in the LES, the TKE builds up along the streamwise direction within the wind farm and then drops. Whereas in the mesoscale simulations, the TKE cannot build up. And furthermore, there's the TKE drops much faster in the near farm wake. And interestingly, this is also related to the spatial gradients, because the mesoscale simulations don't have the spatial gradients. Okay, first of all, because the TKE drops, it means that the added viscosity will be lower in the wake. So on the one hand, that will limitate the wake recovery, underestimate the wake recovery because of this low TKE, the viscosity drops. That's one thing. So from the things that we saw is that the under-resolved gradients in the mesoscale simulations, they inhibit wake recovery in two ways. The first one is directly in the spatial gradient. So because of the coarse resolution, they don't have enough spatial gradients. And in this sense, they will underestimate the gradients and thus the momentum fluxes that are related to the wake recovery. And the other way is indirectly in the added viscosity, because the TKE drops and then the added viscosity drops, and then you also reduces this term. Okay, so to wrap up the talk today on the role of gradients on wind farm power and wake recovery. So first we saw that the horizontal gradients, they produce unexpected power performance patterns. And this situation happens associated with the low-level jets who are very sensitive to the terrain effects and vertical displacements. And second, we saw that different spatial gradients now related to the gradients in the wake itself can slow down the wake recovery in mesoscale simulations, and that's of course important to simulate the big clusters of offshore wind farms. The next steps, we were producing a new set of simulations, LES simulations using fast-eddy, which is a GPU-based model. So extend going beyond the neutral conditions that we just saw and simulating stable conditions and convective conditions, and see how the mesoscale simulations simulate the wake effects. I'll stop here, and thanks for listening.
Thank you, William. Oh, that was great. So are there any questions from the audience? Let me check the chat here. Yeah, so I can start. I had a few questions. So I was just curious if you could talk about the like sort of the purpose of the simulations. Is the goal to try to sort of optimize the placement of wind turbines, which this kind of study could inform, or just to kind of better understand what's going on with existing wind farms? Or I was just curious sort of what the driver behind AWAKEN and some of this work is, if there's some, if it's related to improving wind energy collection, for example.
Yes, that's a great question. This study in particular is focused on understanding the physics of what's going on, and making sense of what's going on. And then this information can help, because the wind farm owners, they use models to build the wind farm. So they have numerical model, they have a measurement campaign, they combine both. They have a wind speed map for the region representative of 20 years of wind farm operation, and then they pick, okay, this is the best spot for the turbines, and then we have the wake effects, and they perform some sort of optimization. If these models don't have the physics that we shown here, then that's a problem, because they wouldn't be representing, the wind wouldn't be as representative as it actually is. So that's basically our work, and the AWAKEN work is understanding these physics, perhaps informing engineering analytical wake models to start incorporating these features in terrain effects, and later on the wind farm owners.
Okay, and then I was curious. So in terms of the time scales of this, I think you're looking more at sort of like weather time scales. Correct me if I'm wrong. I was curious if there's an interest in longer term, like more, well, maybe not climate. I mean, years would be a lot, but like slightly longer term simulations of what you're doing here. Because I think here, how long were these? How many days did you simulate?
The simulation for AWAKEN, it was actually a single hour, so that's very.
Just I thought it was longer than that. Okay.
Yeah. I mean, the whole simulation, like the spin up of the mesoscale domains, it takes like 1 day or something. But the actual analysis with the LES and the turbines, that's 1 hour. So that's.
Oh, no, sorry. I think you misunderstood my question. How many, like, what's the time frame simulated in the simulation? Like, are you simulating the turbine over a day or 2 days, or not how long it took to run?
Yeah, 1 hour.
Okay. It's only 1 hour. Okay.
Yeah.
I
So
guess maybe that's to understand some of these things. Maybe that's sufficient, and you don't need something longer term, because that's
yeah,
interesting.
actually, longer term, of course. I mean, if we could, we would go longer, but it's so expensive,
Yeah.
that's one of the reasons that we're using now these GPUs based models like FastEd. With FastEd, you can run perhaps giving a certain diurnal cycle, perhaps, or a few diurnal cycles. Worth LES at 5-meter resolution, you can do that. It's too
Okay.
expensive.
And then I was like, this is maybe a suggestion. You guys have probably thought or talked about this because it's kind of everywhere. But I mean, one interesting idea, you have this super high resolution model, but you can't run it for very long. But I mean, potentially, and the LES has a lot of parameterizations in it to make it cheaper. But I don't know if you guys have thought about like using the very high resolution to maybe create a machine learned model that would go into the LES to improve some of the physics there, or something like this.
Yeah, that's a good idea. We haven't thought about it,
Okay.
but that's a good idea.
Yeah, okay, cool. I don't want to dominate this and we're almost at time, but are there any other questions? Oh, there's something in the chat. Oh, that's not a question, that's just a compliment. Last call for questions from the audience. I guess people are either shy or quiet today, or your talk was very clear, which it was. So, okay, so I think we're at time. So thank you very much, William. Thank you everyone for coming.